The title of my talk is a practical characterization of Epdm by pyrolysis gas chromatography. Here is today's content. After the introduction, I will talk about 4 examples of the analysis of Epdm by using pyrolysis gas chromatography techniques. As you know, Epdm stands for ethylene, propylene, diene copolymer rubber. Due to the excellent resistance to heat, weather aging, and recyclability, Epdm is known as a rubber with a low environmental burden. For that reason, it is extensively used, for example, in the automotive industry as rubber parts and thermoplastic elastomers. My talk will focus on the practical characterization of Epdm by pyrolysis GC techniques. Today, polymer materials are used everywhere, but they go through various processes before they become final products. This chart is a summary of the relationship between the production process and analytical challenges at each stage. First, the monomer is polymerized to synthesize a polymer, and then additives are added to make a raw material, which is then subjected to a molding process to become a final product. After that, some are used and wasted, or some are recycled and used in each process. From the viewpoint of manufacturing and quality control, it is important to analyze the molecular structure of polymers, the composition of polymer and concentration of additives, and structural change associated with photothermal oxidative degradation. Especially for practical polymer materials, it is very rare that the polymer material is used as it is. This is because the polymer material alone lacks long-term storage stability, weather resistance, practicality, and so on. Therefore, it is also important to quantify additives for product improvement and failure analysis. Pyrolysis gas chromatography mass spectrometry Py-GCMS is one of the most promising and practical analytical techniques for the qualification and quantification of polymeric materials because it only requires a trace amount of sample with no sample pretreatment while providing unique information that is unobtainable by the other techniques. A typical Py-GC system is configured with a pyrolyzer installed on the GC inlet, with detectors such as a quadrupole mass detector or FID or FPD or so. So here, 2 analytical methods are used with this system. One is evolved gas analysis, EGA-MS, that uses a 2.5 meter without stationary phase column instead of a separation column. EGA is a method in which the sample is heated in the pyrolyzer and the gas evolved at each temperature is monitored by mass detector to obtain the thermal characteristics of the sample. This is a typical EGA thermogram. The horizontal axis is the temperature of the pyrolyzer furnace. From this result, additives information and polymer information of the sample can be obtained. Based on this information, we will perform qualitative and quantitative analysis of polymers and additives by using separation analysis with a separation column. So same system, but the column is different. So other analytical methods are the pyrolysis GCMS or thermal desorption, so TD-GCMS, and the double shot GCMS method. Double shot GCMS method is the combination of thermal desorption GCMS followed by flash pyrolysis GCMS. These are typical results of TD chromatograms and pyrograms. The pyrolysis method instantaneously pyrolyzed the sample at the high temperature. Let's move on to the first example, structural characterization of Epdm using pyrolysis gas chromatography. This example was done by Professor Tsuge in Nagoya University and his research group. They analyzed composition and chain structure of Epdm by Py-GCMS and developed quantitative analysis method for the diene part of vulcanized Epdm sample. This slide shows the comparison of pyograms for EPM and Epdm before vulcanization. The top pyogram is ethylene propylene rubber EPM sample containing no diene component. The bottom pyogram is Epdm sample containing 12.3% ethylene no boron. Both samples were pyrolyzed at 650 degrees C. When comparing the pyograms, 5 peaks from D1 to D5 which are not observed in EPM samples pyogram appeared between various hydrocarbons peaks generated from ethylene propylene chain. Based on their mass spectrum, the 5 peaks D1 to D5 were identified as C78H or C7H10, which reflects the characteristic structure of ethylene no boron unit. Since relative intensities of the 5 peaks D1 to D5 showed a good correlation with the ethylene no boron content, the calibration curve was created. Based on the calibration curve, the ethylene no boron amount was quantified with a reproducibility of RSD less than 5%. It is noted that this method can be applied not only to Epdm before vulcanization but also to vulcanized Epdm sample. The next example is analysis of cross-linking structure and vulcanization mechanism of sulfur vulcanized Epdm by Py-GC with flame photometric detector. Again, this research was conducted by Professor Tsuge and his research group. In this experiment, 2 samples were prepared. One was Epdm compounded with sulfur only, and another was Epdm compounded with sulfur and 2-mercaptol benzothiazole. I call this compound MBT in the rest of the slides. The top 2 figures show the FID and FPD pyograms of Epdm sample vulcanized by using sulfur and MBT. The bottom 2 figures show the FID and FPD pyograms of Epdm sample vulcanized by using sulfur only. It is noted that the vulcanization accelerator MBT that did not contribute to the vulcanization was previously removed from the both samples by Soxley extraction before analysis. So the pyrolyzed products on the pyogram were derived from the backbone or cross-linked structure of the vulcanized Epdm structure. Looking at the result, bendothiazole, which is a degradation product of MBT, was also observed on the both pyogram. On the other hand, on the pyogram of FPD, two decomposition components, we call it CS, reflecting the cross-linked structure of acetylene nobornen and sulfur were observed. Based on the mass spectrum, these compounds were found to be C7H6S, whose molecular weight was 122, as shown here. The lower part shows pyograms of FYD and FPD, which were measured and analyzed in the same manner using Epdm vulcanized sample with sulfur alone. In general, it is known that the vulcanization rate of sulfur alone is very slow, so here the vulcanization time was extended to 60 minutes, and the amount of sulfur was increased. Looking at the pyograms, the same peak as the top one was observed, but only two CS components were observed in FPD, and no bendothiazole peak was observed in the both pyogram. Therefore, it was found that the two CS components were pyorized components from the cross-linked portion where acetylene nobornen and sulfur were chemically bonded. For the pyrorized compounds detected in the previous slide, how the peak intensity on the pyogram would change as the vulcanization reaction progresses was investigated. These are FPD pyograms after extracting and removing unreacted compounds from the sample, in which the vulcanization time was 2, 6, and 20 minutes. Since bendothiazole peak was already observed in the early stage of vulcanization, the polysulfide compound produced by the reaction between MBT and sulfur formed a pendant bond with acetylene nobornen in the very early stage of vulcanization. In addition, the strength of CS peaks increased as the vulcanization progressed, which reflects the process of forming sulfur bridge structures. The next example is analysis of thermal degradation mechanism of sulfur vulcanized Epdm by Pygiesms. This research was conducted by Professor Tsuge and his research group. The samples were prepared by the following steps. After these additives were blended with Epdm, raw kneading and then press vulcanization were performed at 160 degrees C for 7 minutes, which is close to practical vulcanization conditions. Next, make two types of sample. One is the non-vulcanized, another is the vulcanized Epdm sample sheet with 1.5 mm thickness, and leave them in an air circulation oven kept at 150 degrees C for 96 hours to prepare thermally degraded Epdm samples. The top figure is the pyogram of vulcanized Epdm sample before thermal degradation. And the bottom figure is a pyogram of the Ebdm sample after thermal degradation. In the top pyogram, in addition to many peaks reflecting the ethylene propylene backbone, peaks such as C7H10 reflecting the ethylene no-boron unit were observed around retention time of 5 to 8 minutes. However, in the lower pyogram, the relative intensities of these peak groups were significantly reduced. It is suggested that the thermal oxidation reaction was proceeding in the vicinity of the diene units. Furthermore, a new peak appeared around the retention time of about 15 minutes. This peak was identified as acetyl cyclopentadiene (ACP) based on the mass spectrum. This slide explains acetyl cyclopentadiene generation process through thermal decomposition of vulcanized Epdm. So this ACP reflected the structure in which the side chain double bond of ethylene no-boron unit was oxidized to generate an acetyl group. It was suggested that the oxidative degradation reaction preferentially occurred in the side chain double bond, which has a relatively high reactivity. This slide shows the relationship between peak area and degradation time of ACP decomposed from Ebdm. When comparing the peak intensities of ACP by different thermal degradation time, it was observed that the relative peak intensities of ACP ended up with decreasing. It was suggested that due to thermal degradation, acetyl group once generated on the ethylene no-boron unit was further decomposed as the heating progressed. Therefore, acetyl cyclopentadiene (ACP) could be the index for thermal oxidative degradation of vulcanized Epdm and could be used as a marker compound. The last example is rapid evaluation of photothermal and oxidative degradation of Epdm by online UV irradiation Py-GCMS. Polymer materials are known to degrade gradually in their physical and chemical properties by prolonged exposure to light, heat, oxygen, moisture, mechanical stress, and environmental pollutants. Photo and thermal degradation of polymer under oxidative atmosphere is usually caused by radical formations through polymer chain scissions and or side chain elimination followed by oxidative chain reactions. Conventionally, outdoor exposure test and weather meter test have been used to estimate a product life of polymer products. However, both test methods take a few weeks to years. Also, not only the structural change of the sample after degradation or during degradation process, but also decomposed volatile compounds formed from a sample have been the important target or information. However, there was no method to collect these decomposed volatiles during the degradation process. So the challenges of the conventional tests are to reduce testing duration, identify the volatiles during the degradation process, and understand structural change of the degraded polymer products. So to overcome these challenges, we developed online UV irradiation pyrolysis GCMS or UV Py-GCMS system to complement the conventional tests. In this talk, we use the system to study the photo, thermal, and oxidative degradation of Epdm sample. The configuration of UV Py-GCMS system is shown here. UV light from xenon arc lamp is delivered via an optical fiber cable to the center of the pyrolyzer furnace. The sample placed in a sample cup is directly irradiated. This is enlarged figure. UV light, and here is sample cup, and this is sample. The sample can be heated to any desired temperature under, for example, air during UV irradiation. Photothermal oxidation-induced volatile degradation products are then cryotrapped by immersing a short length of the column head into a liquid nitrogen. The condensed volatile components are then analyzed by GCMS. In addition, the residual degraded polymer sample in the sample cup can be analyzed by either EGMS or Py-GCMS afterwards. The EGA thermograms of the sample before and after 1 hour UV irradiation are shown here. When we compare data before and then after irradiation, we compare peak height, peak top temperature, half height width, and peak tailing. After 1 hour UV irradiation, the peak height decreased and peak top temperature shifted lower temperatures by 10 degrees C, and the half height width increased from 30 degrees to 50 degrees C. So we plotted the relationship between irradiation time versus peak height, peak top temperatures, and half height width. As irradiation time increased, the peak height decreased, and the peak top temperature also decreased or shifted to lower temperatures, whereas half height width increased as irradiation time increased. So these results indicates that the degree of photothermal and oxidative degradation of Epdm could be evaluated using the peak height, peak top temperatures, and the half height width of the peak in the EGA thermogram. These are the chromatograms comparing the volatiles formed without UV radiation and with UV radiation for 1 hour at 60 degrees C under air. With UV irradiation, a number of volatile compounds formed, and acetaldehyde, acetone, butanone, acetic acid. They are originated from the propylene content. Also, straight-chain aldehyde, such as nonanol, were observed. The photo and thermal and oxidative degradation of Epdm was evidenced by these results. These are pyrograms obtained at 600 degrees C without UV radiation and with UV radiation for 1 hour, 12 hours, and 24 hours. The peak intensity decreased as UV irradiation time increased. It may be attributed to the degradation of Epdm copolymer with UV irradiation time. Let's take a closer look at the peaks highlighted with yellow background here. These are enlarged pyrograms obtained at 600 degrees C without UV radiation, with UV radiation for 1 hour, 12 hours, and 24 hours. Comparing the pyrograms, the peak for CO2, which was not observed before the UV irradiation, was observed, and its intensity increased as the UV irradiation time increased. This is a plot of peak area of CO2, butane, and hexane versus UV irradiation time. CO2 peak was not found at the without UV time, but the peak intensity of CO2 increased as the UV irradiation time increased. It indicated that the oxidation of Epdm produced CO2 as the backbone structure decomposed. In summary, I introduced practical characterization methods for vulcanized Epdm. Py-GC or Py-GCMS techniques can be applied to not only Epdm but also other rubber material developments, competitors' product analysis, product quality assurance, or failure analysis of your products. Thank you very much for your attention.